Hello, everyone. Welcome back. Welcome back to CS 700, Computer Science of Continuous Data Algorithmic Foundation of Numerics. So last time we have characterized some common operators in numerics in terms of discrete complexity class. And with characterized, I mean showed that these operators map functions that are polynomial time computable to functions that belong to this complexity class, for example, belong to P space. And we've shown that this is optimal. We have constructed polynomial time computable functions such that if the resulting function of the operator belongs to a smaller complexity class, then actually this discrete complexity class coincide. There's a collapse, which most people believe is not the case. So let me recall these characterizations, and then we will move on to similarly characterize more advanced operator, namely the solutions operators of two popular partial differential equations. And this is really top notch. This is the current front of research that happens in this lab. Okay, so first, as a reminder, let me turn on the slide sharing. Right, so yes. So this is the maximization operator, parametric maximization, which we've established to characterize the complete discrete complexity class NP, the parametric maximum of a polynomial time or of a smooth function is again polynomial time computable if and only if P is equal to NP. And similarly, the Riemann indefinite integration operator characterizes sharp P for an arbitrary polynomial time computable or even smooth function. Its parametric, its indefinite integral is again computable in polynomial time if and only if fp, polynomial time computable integer function, equals sharp P, polynomial countable integer function. Whereas if we restrict to definite Riemann integration with fixed upper bound, then this functional, not operator, but functional, characterizes the unary complexity class sharp P1. Solving ordinary differential equation turned out to be a little bit more subtle because we need to strengthen the hypothesis in order for the solution to be unique. And if we strengthen the hypothesis in such a way that the right-hand side is Lipschitz continuous or even C1 continuously differentiable, then the solution is unique and characterizes actually the discrete complexity class P space, which is a famous, a celebrated result of Akitoshi Kawamura. And what we're going to see today is two similar characterizations of the solution operator of two linear partial differential equations. And being linear, in one hand, makes the problem possibly easier than solving ordinary differential equation, which, as you recall, had a nonlinear right-hand side. So ordinary differential equation generalizes indefinite Riemann integration. The right-hand side in general is a nonlinear. It's a C1 continuously differentiable functions. But on the other hand, of course, partial differential equation is probably more difficult to solve. There are various indications why partial differential equations tend to be more complicated than ordinary differential equations. Specifically, we're going to look at the computational complexity inherent to Poisson's equation. Here you see Poisson's equation, which is a second order in space partial differential equation. It's a linear partial differential equation. And here we consider the variant of Poisson's equation with given right-hand side inside the, let's say, two-dimensional unit disk. And on the boundary of the unit disk, we need to impose some boundary condition. And the boundary condition we impose here is, for simplicity, zero boundary condition. And here, Florian Steinberg had proven that this is the solution in this case is a classical solution if the right-hand side is polynomial time computable and characterizes Sharpe. And on the next slides, we're going to see and recover his proof of this interesting characterization of Sharpe. So it's basically the same computational complexity as indefinite Riemann integration. On that Florian Steinberg's work, and we're going to similarly see how the heat equation characterizes the discrete complexity class Sharpe-1. So solving the heat equation has the same essential complexity as definite Riemann integration, which is an interesting subtlety. So here for your memory, and we're going to investigate this more thoroughly in the course of today's lecture. Here's the heat equation. The heat equation has a designated variable which is commonly denoted time. So it's second order in space, first order in time. And we have not an inhomogeneity as in Poisson's case, but instead we have a non-trivial initial condition f, that is the argument, the input parameter to the PDE. And we're going to consider the heat equation on periodic d-dimensional hypercube with periodic boundary conditions. So remember, we need compact domains in order to even have a meaningful complexity theory. And here, by making it periodic, we obtain a compact domain. And here, this is a very recent work, joint work with Svetlana, and with Gleb Pogudin, and with Ivan Kosvara. This characterizes the unary complexity class Sharpe-1. Okay, let's look at the proofs of these two characterizations, and the proofs will actually make use of our previous characterizations. So we're going to perform what is later going to formalize as a polynomial time reduction of continuous function problems from one function problem to another function problem. And this notion of continuous polynomial time reduction was actually introduced and invented by Akitoshi Kawamura in his PhD thesis as a complexity theoretic strengthening of computable continuous reduction, which is also known as Weierauch reduction, because that was introduced and invented by Klaus Weierauch. But here in this chapter of the lecture, we're still going to restrict to intuitive notion, and only later, based on this example, we're going to formalize this notion of continuous polynomial time reduction. Okay, so Poisson's equation. What's up with Poisson's equation? So Poisson's equation is this linear second order partial differential equation here with given right-hand side and considered on the Euclidean unit disk. So here you see, for example, the two-dimensional Euclidean unit disk. Inside the unit disk, the second derivative, sum of second partial derivatives of the solution U must equal the given right-hand side f, and on the boundary, the solution must vanish. So, and here we have this Laplace operator, the sum of second spatial derivatives twice with respect to x, twice with respect to y, and so on. And recall that second derivative basically captures the geometric condition of curvature. And that is true also in higher dimension as here. So we can imagine the geometric meaning of this the partial differential equation that f prescribes a certain curvature, right? And so prescribing a curvature in one dimension basically means that taking the first integral, that means we have prescribed the slope, and integrating a second time, taking antiderivative a second time, then we have recovered the original function, the solution. And here in higher dimension, of course, the situation is a little bit more complicated. Actually, even the question of whether there exists a solution U to any given, let's say, continuous right-hand side is a subtle question. But here, to support your intuition, here's a picture. So the solution here vanishes on the boundary, right, because of this boundary condition. And inside it, there's this bulb that arises from the prescribed curvature. So here the curvature is very small, right? A large radius of curvature. And here's a small curvature. So the small radius, so it's strongly curved. So yes, as I mentioned, the theory of mathematical theory of partial differential equations is much more involved than that of ordinary differential equations. Such questions as existence and uniqueness of solution is much more delicate. And there's this famous counterexample to Louis from 1957, who constructed an admittedly artificial partial differential equation which does not have a solution. And that's quite astonishing because if you, for example, input his PDE into a common numerical solution solver like MATLAB, then the computer will readily output some plot of a purported solution. But of course, we as mathematicians know that this plot cannot be trusted because the theory says there is no solution. So this is kind of again a warning from the pitfalls of naive numerics. So when the computer produces some output, that can mean all or nothing unless a properly trained mathematician looks at it. And one of our goals of research is to put this background knowledge into a computer so that when the computer does output a solution, we can actually trust the solution. Let me also point out that the similar question of existence and uniqueness of solution and continuous dependence is actually one of the millennium problems when with respect to the nonlinear Navier-Stokes partial differential equation. So now I've repeatedly referred to existence, uniqueness, and continuous dependence of solution, and this is what Hadamard has summarized with the term well-posed problem. So the solution must exist, the solution must be unique, and the solution must depend continuously on the data, where data can mean initial condition or data can mean boundary condition. And also when referring to existence and uniqueness, these are meant to refer to a certain function class. And in a sense, the art of partial differential equations as a pure mathematical discipline is to find the proper function class such that in this function class, the solution exists and is unique and depends continuously with respect to the metric with which we equip the function class. So kind of turning the problem around, if we don't have a well-posed problem, then find the proper function class which makes the problem well-posed, and this is called maximal regularity. And for the Poisson's equation, to which we now return, for example, classical solution is not the proper function class. Classical solution would mean, right, so if we have a continuous right-hand side, then having second derivatives on the left-hand side, classical solution would mean that the second derivative should be continuous. That is, a classical solution would be one which is twice continuously differentiable. And Petrini, over 100 years ago, showed that in general, this is not what we can expect. In general, there exists continuous right-hand sides for which there exists no classical, no twice continuously differentiable solution. And this had forced mathematicians to resort to more sophisticated, more complex function spaces, such as Sobolev space functions with the weak derivatives, which are integrable. But fortunately, right, yeah, weak integrable Sobolev solutions, and the complexity theory of such advanced function spaces is still under development. We cannot currently even have the proper notions. We're working on identifying the proper notions for such advanced function spaces. So how can we still study the complexity of Poisson's equation if we don't have complexity notion for the function space? Actually, fortunately, Florian was able to prove in his PhD thesis that in our case, the problem does not arise, because he proved that as long as the right-hand side function is not just continuous, but polynomial time computable, from that we know that the right-hand side has a polynomial modulus of continuity, and this is sufficient to guarantee a classical solution. This is sufficient to make Petrini's counterexample vanish. So the first part of 3 parts of his main breakthrough result in his PhD thesis is that under this hypothesis, the solution exists and is classical and unique. And the emphasis is on being a classical solution. And for classical solutions, for classical functions, for once or twice continuously differentiable functions, we have our existing complexity theory, as we have seen at the beginning of this chapter 5 of the current lecture. So I'm not going to prove this part because it's essentially a purely mathematical part. The hypothesis that the right-hand side has a polynomial modulus of continuity is the key ingredient here. Then Florian went on to prove the complexity characterization that we've already meant before, namely that the solution is polynomial time computable provided that the complexity hierarchy collapses at the level of sharp B, namely if Fp is equal to sharp B, then the solution is computable in polynomial time, just like indefinite Riemann integration was polynomial time computable if Fp is equal to sharp B. And let me remind you that this is a non-uniform result. So as with Riemann integration, we would fix the polynomial time computable integrand. Here we would fix the polynomial time computable right-hand side. The question of dependence on the right-hand side, how leads to the question of how can we input such a complicated object as a function into an algorithm. And so far, we've only talked about how to input and output real numbers, but not how to input and output entire functions. And as you recall, inputting a function in terms of sequence of Weierstrass polynomials is suitable for computability investigation, but for complexity investigation, it makes little sense because, or even inputting such a polynomial of necessarily exponential degree requires exponential time. And so we cannot have any polynomial computation when we encode the input functions as the Weierstrass polynomials. But this will later lead in the next chapter to a kind of higher order coding and complexity theory. But for now, this problem does not arise because we fix the function and thus don't need to talk about how it's encoded or input. So the baseline is, so under this strong hypothesis, the solution is polynomial time computable. And third important contribution of Florian Steinberg, this is the optimal hypothesis, namely there exists a polynomial time computable and actually even a smooth right-hand side function such that if the solution U is polynomial time computable, then these two discrete complexity classes coincide and there's a significant collapse happening in the complexity hierarchy. So this is what we mean with Poisson's equation characterizes sharp P in shorthand, but let me also point out that this short statement is actually a drastic oversimplification of the actual statement, which refers to a particular shape of the domain and a particular kind of dependence of the solution operator. Maybe here we have an inhomogeneous right-hand side, and we have a Dirichlet problem where we impose a zero condition on the boundary. Okay. So let's now move on to prove the complexity theoretical two statements of Florian Steinberg's characterization. Namely, we're going to skip over the part that the solution is a classical one, and on this slide demonstrate that if Fp is equal to sharp P, then the solution is actually computable in polynomial time. Okay, and to this end, we're going to recall in use without proof a fact, a generic kind of solution of Poisson's equation based on the Green's function. And the solution is known to be given by this integral with a given right-hand side f weighted by the Green's function, where the Green's function depends on, well, being the Poisson equation and also is specific to the domain. So for a different domain, the Poisson's equation has a different Green's function. And for some domains, it's easy to, it's an exercise actually to write down explicitly the Green's function. And this is one of those domains where using the method of mirror charges, one can arrive at this explicit solution of the Green's function. It's the difference of two functions, and these functions in turn are the so-called fundamental solution of the homogeneous Poisson equation. Namely, in dimension 2, it's basically the logarithm, or the negative logarithm in this case, scaled for some normalization purposes. And starting with dimension 3, it's the 1 over r potential that occurs so often, Coulomb potential, Newton potential. These all are basically because of Poisson's equation. So, right, and again here we have some normalization constant that depends on the dimension, but this it's not further of interest for us. Well, it's a polynomial time computable constant, but we don't need to know more because we're going to fix also the dimension. Since we fix the function, also the dimension is fixed. So to summarize, mathematics has provided us with kind of an explicit expression for the solution, right? So here, this is explicit up to the constant. This is explicit, take the difference, and then this integral. So why is this hard to compute? I hear numerical scientists say, well, because of this integral, of course, right? We know that integration is a hard problem. So let's look more closely at this integral. Well, first it's a high dimensional integral. It's an integral in dimension d, so it's a iterated one-dimensional Riemann integral over the Euclidean unit ball. And also what makes this integral, which is already complicated, right? Riemann integration, sharp p. But we're not done yet, right? That would be an easy argument to say it's computable in sharp p because this is a Riemann integral, but there's an additional obstacle, namely this Green's function has a singularity. So this is not even a Riemann integral, it's an improper integral because you see here for r equals 0, here in dimension 2 and in dimension 3 on every dimension except for 1, there's a singularity when x is equal to y. There's a division by 0 basically, right? So this is not a continuous integrand. It has a singularity. It's a removable singularity. That's part of the solution theory. So integrating over continuous function like this results in a well-defined but still an improper integral. Right here, so you can see a picture of this singularity as the function tends to infinity when x is equal to y. So although we know that indefinite Riemann integration is in sharp p, this is not indefinite Riemann integration because the singularity, it is an improper integral. It's a limit of a sequence of truncated integrals. And we know that with limits, we have to be careful because limits can leave even the realm of computability, not to mention polynomial time computability, according to Specker's example. So what Florian did in order to establish that also this particular improper integral is indeed computable in sharp p, is he would truncate the integral. He would cut off the singularity at some carefully chosen radius around the singularity, or cut off this peak at a certain height, carefully chosen, so that his error analysis guarantees that cutting this off at this height, well, cutting it off does produce a Riemann integral, right? So making here kind of like a platform, then the resulting integrand is continuous, but of course it has changed. And then bounding change, bounding the error introduced by this kind of cutoff. And then Florian showed that by cutting off at a carefully chosen height, the error remains bounded by 2 to the minus n, and the function after the cutoff is still sufficiently well behaved. It will have large values, but not too large values, so that the integral, the now proper Riemann integral, can still be computed in sharp p. So that's kind of the gist of Florian Steinberg's proof that Poisson's equation can be computed in sharp p in basically. Okay, and that being said, now of course the natural question is whether this is optimal, and you already know the answer because that's the third and last item of this great result. Namely, yes, it is optimal. There exists a polynomial time computable, even a smooth right-hand side, for which polynomial time computability of the solution U does imply that the two discrete complexity class actually coincide. There's a collapse of the hierarchy, and the hypothesis that Fp is equal to sharp P is optimal. And to this end, let's recall that in what sense indefinite Riemann integration is sharp P complete, namely in this sense, there exists this polynomial time computable function whose parametric integral, indefinite integral, is polynomial time if and only if Fp is equal to sharp P. And we're going to use that and kind of encode not arbitrary sharp P problem as we did when we proved and constructed the existence of this function, but instead we're going to encode this function itself into the right-hand side of the PDE, right? This is later going to be formalized as continuous reduction. So this is kind of corresponds to the mass reduction, encoding an arbitrary, discrete counting problem in sharp P into this continuous function. And now in turn, we're going to encode this continuous function as right-hand side of the Poisson's problem. That's all. That's what Florian Steinberg did. But we're going to need to make some adjustment of this function g. We need a little bit stronger properties than just being polynomial time computable. So imagine like this, where the function g, and actually we will make some changes. But let's first look at the kind of implicit reduction, namely how does Florian define the right-hand side f? First of all, he restricts to radially symmetric right-hand sides f. Remember, f here lives in the two-dimensional or in general on the d-dimensional unit disk. So the argument to f is actually a real vector, and f Florian considers and restricts to right-hand side which depend only on the length of said vector, not on the other aspects like the direction of the vector. This is what's called radially symmetric function. Depends only on the length of the argument. And in this case, by symmetry considerations show that also the solution will be radially symmetric, which makes sense because there's no reason or cause for possible symmetry breaking. Okay, so and since both right-hand side and solution are radially symmetric, we're fortunate that the Laplace operator simplifies significantly, right? So there's this complicated formula for the Laplace operator in spherical coordinates. In rectangular coordinates, it's the second derivative with respect to x plus second derivative with respect to y and so on. But in spherical coordinates, it's more involved. But if the angular derivatives vanish, which they do here, because if we're talking about the radially symmetric case, there is no dependence on the angle at all. It simplifies again and becomes an ordinary differential operator of one parameter, namely the radius, the distance from the origin, which we here denote r. So in this case, Poisson's equation simplifies to an ordinary differential equation, this one. So here's the radially symmetric right-hand side, and the Laplace operator becomes this ordinary differential equation, differential operator and observe. Yeah, if you want to understand why this looks like this, recall that in spherical coordinates, change of coordinates in high dimension, there's always this determinant of the matrix of partial derivative, the Jacobian, right? And if you do the calculation, your math, the Jacobian then looks like this. So this second order ordinary differential operator, but it's a nonlinear differential operator. It depends nonlinearly on the argument r here. And so here it's a multiplication, and here it's a division. Okay, we're just going to use that because now we can kind of solve this ordinary differential equation, right? Namely, the solution then will, right, in order to remember, we want to encode the function g, which is hard to integrate, into the right-hand side f, and Florian encodes it in this way. Take the function g and divide it by r to the t minus 1. And now here it says this is polynomial time computable, and that should immediately raise question, because obviously there's a division by 0 problem here when r tends to the center of the unit disk, right? Then there's division by 0. So this is not even well defined in general, not to mention polynomial time computable. Remember, in order to even have a complexity bound, we need a compact domain. And here we're forced to remove the origin from the domain to make this well defined, and removing the origin from this unit disk, the result is not compact anymore, right? Yeah, origin is crucial for this to be compact, of course. And now comes the already announced massaging modification of the function g, which is known to be hard to integrate, easy to compute, but hard to integrate. Namely, the first thing is we're going to make sure we're going to extend that function such that it actually vanishes at 0. Okay, 0 is the problem. If this function vanishes at 0, then we're kind of good. Of course, 0 divided by 0 at least has a chance of being defined. So actually we want, of course, more. We want the resulting function to also be not just well defined at 0, but also continuously differentiable and maybe even smooth later. But first of all, let's make it well defined by observing that it is no loss of generality that the function here we consider actually vanishes at 0. If it doesn't, then we can easily kind of extend it, kind of shift it in x direction to make room, and then in this room extend it towards reaching the x-axis like here. And the second massaging is we can even further extend it, so not just at the origin the function is 0, but it's actually 0 on an entire small interval, but small but of positive measure, like this here, like 0 from 0 to 1 over 4, by again shifting the function and extending it identically 0. And now everything here finally works out. Now we can safely divide by 0, because when we do, when r is equal to 0 or close to 0, then already for a long time, the argument, the numerator had been 0 all along. And so we can safely state and compute in polynomial time that fraction, because now the division by 0 problem has vanished already at r equal 1 over 4, and even more when r tends to 0. Good. So, and why did Florian choose this way of encoding this hard to integrate right-hand side g into right-hand side function f? Because of this equation, right? because now both sides contain this division by r to the d minus 1. So they cancel, and we arrive at this ordinary differential equation. There's a prime missing here. It's still second order. But now we can integrate that and arrive at the following solution. So the scaling times the solution must be equal to the antiderivative of the original right-hand side, g. And remember, this is the part that is hard to compute. The integral is hard to compute. And this is exactly what happens here. Whereas if we could compute the solution u in polynomial time, then we could also weight it, scale it with r to the d minus 1 in polynomial time, and thus recover the integral. So that indeed, in this sense, we have kind of continuously reduced the function g, which is hard to integrate and satisfies the additional properties, to the right-hand side of the PDE, so that the solution allows us to recover the indefinite Riemann integral, which by hypothesis we cannot. So this is concludes the proof that the Poisson's equation, computing it in Sharpie, is indeed optimal, is best we can hope for, and smoothness does not help. That's an important observation as usual. Okay, so that concludes our discussion of the intrinsic complexity of Poisson's equation. And now we're ready to move on to similarly discuss the heat equation. Okay, heat equation is here. Heat equation is this partial differential equation, first order time. That is means it's an evolution equation. It means that the solution function will evolve over time. It will depend on both the space, second order in space. It's still this Laplace operator that prescribes, as you recall, the curvature, right? And the curvature is now not given externally by some right-hand side, by some inhomogeneity, but here we consider the homogeneous problem. The curvature is here now given by the temporal derivative of the function, or no, it's the opposite. The curvature provides the temporal derivative. The curvature is what drives the evolution of the equation. And we consider this equation on the d-dimensional unit cube with periodic boundary conditions. So here's, let's say, the unit cube in dimension 2, which is a square. And periodic means that if we leave the square towards the top, then we re-emerge from the bottom. And if we leave the square to the right, then we re-emerge from the left, and vice versa. So this is actually a common topology, popular topology in computer games. So if you're a computer gamer, you may have seen this in many computer games, such as Asteroids, for example. But mathematically, this amounts to a torus. So this is topologically equivalent to a torus. And well, here the difference, the ratio between the diameter here and this diameter should be, of course, be same, which is hard to visualize. So this is a topologically equivalent picture, but not a metrically equivalent picture. But long story short, consider the heat equation on the unit cube with kind of periodic boundary conditions for the function, for the initial condition u0, and for all its for the solution with all its spatial derivatives that will become relevant in a few minutes. So here's a picture, an animation of how the heat equation, what kind of evolution it initiates, and the physical meaning of the heat equation. Why is it called heat equation? Imagine some two-dimensional body, like here, some plate, and part of the plate is initially heated. So this shaped part is initially somehow heated up, like with an iron, and then we watch how this heat evolves over time, how the temperature at each point of this two-dimensional plane changes, and intuitively, well, the heat will dissipate, right? It will distribute itself from the hot parts to the cold parts. So the cold parts will become warmer and the hot parts will become colder. And this making this rigorous and quantitative results in this kind of funny melting behavior. Actually, it's a smoothing behavior, and the smoothing has been well studied rigorously and quantitatively, and we will actually use that quantitative smoothing behavior when we prove optimality of our algorithm for solving the heat equation. Okay, so okay, this is a heat equation, and here's a fundamental solution of the heat equation. We call fundamental solution. We had talked about fundamental solution of Poisson's equation, which was the logarithm in dimension 2, or 1 divided by r in dimension 3, and 1 divided by r squared in dimension 4, and so on. And similarly, this is the fundamental solution of the heat equation, which you can easily verify that this satisfies the heat equation. So what you see here is k is some vector, let's say some integer vector, d-dimensional vector. X is the space coordinate, right? So here, for example, this is dimension 2, or this is dimension 2. And this is the inner product of this integer vector with the spatial vector x. Right, and this is scaled with 2 pi I and raised to the Euler's constant. And here's minus 4 pi, this should be pi squared, times t times k squared. K squared means the sum of the squares of the components. So basically the Euclidean length of the integer vector k squared. And so if we take derivative with respect to t, then minus 4 p squared, remember typo, 4 minus 4 p squared k squared comes here according to the chain rule of differentiation. Whereas if we differentiate twice with respect to space, then twice vector k, integer vector k, comes here, and twice 2 pi I comes here, resulting in 4 pi squared, and I squared is minus 1. So the same factor. So indeed, here, first derivative with respect to time equals second derivative with respect to space. And that also holds in higher dimension, sum of second derivatives. Okay, so this is indeed a solution, and it's a fundamental solution. In particular, it's a periodic solution, right? So if we here add 1 to the argument x, then because of the periodicity of the exponential function, the whole value will not change. So this is really a nice periodic function with all its derivative. It's a well-defined function on the torus. And since we have a linear partial differential equation, whenever we have a solution or several solutions, then any linear combination of these solutions will again be a solution. So we make what is known as a Fourier ansatz for the solution, a linear combination with arbitrary real or complex number coefficients ck, where, as you recall, k is this integer vector. And you also see why it's called Fourier ansatz, because if we omit, for example, the time depends, if we plug in t equals 0, then this is just your ordinary Fourier series, and the ck are just the Fourier coefficients of this periodic function. So this is our ansatz, and now we need to determine the three parameters of this ansatz, the Fourier coefficients ck, and of course the ck can be derived from the initial condition, right? So if we plug in t equals 0, then we, on the left-hand side, arrive at the initial condition u0, right? And on the right-hand side, this part vanishes, and we arrive at this classical Fourier series. So that means if the Fourier coefficients are given, then we can immediately write down the solution. If the Fourier coefficients are not given, but the initial condition function u0 is given or fixed, then we can recover the Fourier coefficients from the Fourier integral, right? So Fourier integral here with a minus, right? Complex conjugation is the inverse. The Fourier transform is inverse to its own adjoint. So this is how we can determine the Fourier coefficients. And once we have the Fourier coefficients, we also have the solution. So let's now look at more closely. Computing the Fourier coefficients amounts to a Riemann integral, right? So at least if the initial condition function u0 is a continuous function, this for sure is a continuous function, then this integral over this torus is a classical Riemann integral, and therefore computable in Sharp-1. Why Sharp-1? Because this is a definite Riemann integral, right? So the dependence here is on k, and k, remember we discussed the difference between strongly polynomial time computable sequences and polynomial time computable sequences. Here we have a polynomial time computable sequence. So when k is given in unary, this is a definite integral and therefore computable in Sharp-1. So that's going to be helpful in a few minutes when we analyze the computational complexity of an implicit algorithm for computing this. Well, it's a simple implicit algorithm. First, take the initial condition, then calculate their Fourier coefficients, and how many I'm going to say in a few minutes. Each one computable in Sharp-1, and then put them together into this sum to recover the solution. And again, question is how many terms of this infinite series do we need to take into account to get a reasonably good approximation of the resulting classical function. Right? So in general, when we talk about Fourier series, we only can expect L2 square integrable functions, but when the initial condition is continuous, then the Fourier series is actually bounded, right? Because the right-hand side is obviously bounded by 1, right? And the domain is bounded. So if the initial condition is continuous, then and bounded, then the Fourier sequence is bounded. And if the Fourier sequence is bounded, then actually this solution is analytic in X, in the spatial variable, for every fixed t greater 0. Why is that the case? Well, because of this here, right? You see here, when t is arbitrary but positive, right? Only very small but positive, then this here means that everything, the terms in this sum decay exponentially fast, actually with e to the minus k squared, right? So in order to get a good approximation, that means we only need the first linearly many terms in that sequence, because the tail converges exponentially fast, faster than a geometric series. So we can do the same analysis as we did for analytic function. Okay, so that we have the following theorem. If the initial condition is polynomial time computable and in particular continuous, then the sequence of Fourier coefficients is strongly computable in sharp P1. So strongly, recall, means index is given in unary, and computable in sharp P1 means if fp1 is equal to sharp P1, then the Fourier sequence is computable in polynomial time, right? Yes, sharp P1 because this is definite Riemann integration. That's the first statement of the theorem. The second statement says under this hypothesis, also the solution is computable in sharp P1 for every positive but fixed time. Right. So as the time tends towards 0, of course, the solution is still analytic, but with worse parameters, right? Because as we reach t equals 0, the solution is not analytic anymore. It's just continuous, just polynomial time computable, right? So this is kind of a non-uniform claim. Fix a positive time, then the solution is analytic and computable in sharp P1 with respect to the space variable. Space variable varies. Time is fixed, positive, arbitrary, but fixed. So that's the kind of positive part. And now for the optimality, the negative part says sharp P1 is indeed the best we can hope for every fixed time t greater 0, if the solution can be computed in polynomial time in fp1 in unary polynomial time, then actually fp1 is equal to sharp p. We say that again. If the solution exists an initial condition u0, which is polynomial time computable, such that if the solution is computable in polynomial time, then actually fp1 coincides with p1. Just the same claim, kind of statement as we had about definite Riemann integration. So let's prove that. I already gave the proof for item A, like here, gave the proof of item B, which follows from this, because we only need polynomially many of these coefficients, and therefore polynomially many terms, because the tail vanishes, tends to 0, so very fast. And it remains to prove for item C, the optimality. And for optimality, recall that for analytic function, we can compute Riemann integrals in polynomial time, right? We can do that by termwise first recovering the coefficients. Yeah, actually, for polynomial time computable analytic function, we can recover its Taylor coefficients. And from Taylor coefficients, we can integrate termwise and thus also compute Riemann integrals. And this means if the solution here is computable in polynomial time, then because it's analytic, it means we can also recover the Fourier coefficient, and in particular, the zeroth Fourier coefficient. And what is the zeroth Fourier coefficient? The zeroth Fourier coefficient is just the integral over the initial condition. And the initial condition is not analytic, it's arbitrary polynomial time. And in particular, the initial condition can be, and we choose in our proof, the initial condition, this easy to compute but hard to integrate function. So when k is equal to 0, this part vanishes. It's just the average. It's just the integral. And this is exactly what is hard for the function we discussed. So if the initial condition is this function, which is easy to compute, but sharp P1 hard to integrate over the definite range, then this is exactly the zeroth Fourier coefficient, which if the solution could be computed in polynomial time, and since it's analytic, could also be computed in polynomial time. So behind this argument, there's the observation that the integral over the solution, the spatial integral, the zeroth Fourier coefficient will not change over time. So the zeroth Fourier coefficient is when k is equal to 0, and you can see here, this does not depend on time. When k is equal to 0, this term doesn't matter. Okay. So to summarize, yes, the heat equation also is hard. It also characterizes a discrete complexity class, but a different one from the Poisson's equation, subtly slightly different. Poisson's equation characterizes sharp P, and heat equation, interestingly, characterizes sharp P1, unary sharp P. And it's an important question whether this is a general phenomenon for linear partial differential equations, or whether this is a kind of a random or an ad hoc observation, whether it really depends on the particular version of the problem we consider. So for Poisson's equation, we would consider the inhomogeneous problem with zero boundary condition. For heat equation, we would consider the homogeneous problem with non-zero boundary condition. And so hopefully a similar investigation that is currently in progress regarding the wave equation will give more insight about the intrinsic computational complexity of partial differential equations. So that wraps up our chapter 5 on complexity theory over the reals. Let me recall, we've talked about notions and properties of polynomial time computable real numbers. Among the 3 definitions for computability, only one actually turned out to be suitable for complexity investigation, namely the one of approximations by dyadic rationals. We talked about polynomial time computable real functions, and again, among the 3 equivalent definitions for computability of real functions, 2 turned out to be equivalent and up to polynomial time and suitable for complexity investigations, namely the transformation definition, with the subtlety that the running time must depend only on the output position, not on the argument, and equivalently the polynomial time computable sequence, not a strongly polynomial, but a polynomial time computable sequence, and having a polynomial modulus of continuity, not necessarily computed, but a polynomial modulus of continuity. Those 2 were equivalent definitions, and from that we've derived interesting properties of polynomial time computable real functions, and in particular the observation that while quantitative computability corresponds to or requires qualitative computability requires qualitative continuity, quantitative complexity requires or induces quantitative continuity, namely polynomial modulus of continuity. And from that on, we have discussed operations that preserve polynomial time functions, in particular like pointwise operations or differentiation, interestingly, when the resulting function is polynomial time computable. Join operation preserves polynomial time computability. But there were also operations for which we didn't know. Before returning to that, we looked at the computational complexity of polynomial time computable real sequences and strongly polynomial time computable real sequences. And as you recall, the difference here was whether the sequence index enters in binary in its length into the running time, or enters in unary, enters with its value in the polynomial runtime bound. And in particular, polynomial time computable real sequences were those that arise from one of the characterizations of polynomial time computable general real functions, where strongly polynomial time computable real sequences were the sequences of coefficients to polynomial time computable analytic functions. Then we looked at operators that preserve polynomial time computable analytic functions, and it particularly saw that Riemann in or definite Riemann integration preserves polynomial time computability for analytic functions, and parametric maximization preserves polynomial time computability for analytic functions. Whereas if we consider the similar problems for general and in particular for smooth functions, then both maximization, parametric maximization, and integration turned out to be much harder in the sense that they actually characterize discrete complexity classes and famous open problems in discrete complexity theory, namely parametric maximization characterizes NP indefinite Riemann integration, characterizes Sharpie, and definite Riemann integration characterizes unary Sharpie1. And when we proved that, we first devised and analyzed the upper bounds algorithms that compute maximization in NP by subdivision as traditional numerics. But the interesting thing is that if P is equal to NP, then we can, although the size of the subdivision is exponential, then still we can recover polynomial time algorithm. Similarly, if Fp is equal to Sharpie, then although the size of the subdivision of the Riemann sum, the number of terms in the Riemann sum is exponential, we can still obtain a polynomial time algorithm. And similarly for definite Riemann integration, where the upper integration bound is fixed, we can get away with the weak hypothesis that Fp1 is equal to Sharpie1. And then we proved right-hand ordinary differential equation solving using classical Euler's method, or interesting using the advanced Runge-Kutta methods. Runge-Kutta is indeed faster, but by most a polynomial factor. And in our complexity picture, this is not sufficient acceleration to improve from, let's say, P space to polynomial time. And indeed, complexity analysis says that Euler's method and Runge-Kutta method are both P space algorithms in the rigorous sense. And then we proved that at least the first three characterizations are optimal, and that these three problems are kind of complete, although completeness and reduction does not yet apply to the continuous setting. This is something we'll talk about later in the course of this lecture. So maximization in this sense is actually possibly easier than integration, unless the hierarchies collapse. And finally, we apply these characterizations of simple numerical operators maximization in and definite integration to advanced solution operators of partial differential equations, where already the notion of the solution in general has to be very carefully investigated. And yeah, so the general picture is characterize discrete complexity classes in terms of numerical problems. And we have seen here some selected example problem. There's a much richer variety of such results ranging up to exponential time. So that's all for today's session. That wraps up, that ends chapter 5. And next time we're going to start with chapter 6 on generic computational complexity on compact metric spaces. as a generalization of the real complexity theory that we've talked about in the past sessions. So thank you for your attention and see you again.